Hey, good morning, everybody. This is Mr. Ainsworth here, and we're going to get into a lesson on end behavior of a polynomial function here. So let's get started. All right, it's called the end in sight. They always come up with some kind of puns for these lessons here. Number one, without evaluating, determine if each expression will be positive or negative. Okay, this is called a sign analysis. Okay, so let's get right into it, and let's figure out, are they positive? Are they negative? Okay, so 100 to the fifth power. Well, 100 to the fifth power is a positive raised to the fifth, and if you multiply 100 times 100 5 times, okay, you're going to get a positive value. Pretty straightforward. Now, if you take a negative number and raise it to the fourth power, all right, you're going to be multiplying four negatives. And visualize this. So if you're multiplying four negatives, uh, there you go. Negative 100 times negative 100 times negative 100 times negative 100. I don't care what the answer is. I mean, we can figure that out. But anytime you multiply two numbers right here, two negative numbers, you get a positive. Okay, and a positive times a positive is positive. So taking a negative number to an even power, and again, this is even power, is always going to end up with a positive result. Whether you raise a positive or a negative to an even power, you're always going to get a positive result. All right. How about the C here? Negative 2 times 800 squared. Well, 800 times 800 is a positive number, but a positive times a negative, well, guess what? That is equal to a negative. All right. All we're doing right now is doing a little sign analysis. Now here, negative 230 to the 17th power, okay, we're multiplying an odd number of negatives. And anytime you multiply an odd number of negatives, like three of them, a negative times another negative here, if you're multiplying negatives together, anytime you have an odd number of them, you're going to end up with a negative number. Because the first pair, a negative times a negative is a positive. That positive times a negative, well, guess what? You're going to end up with negative. So remember that. Anytime you take a negative number to an odd power, you're going to get a negative answer. And the last one here, based on what I just said right here, negative 900 to the fifth power, which is an odd power, well, that's negative. And then you multiply it by negative 6, and you have a negative times a negative. Well, guess what? You have a positive result. Okay, and you've got to be wondering, why is this important? Well, we're going to be substituting big numbers into the dominant term of a function to figure out what happens to the y values. Do they get bigger or do they get smaller or more negative? Okay, and so we'll do that. We're going to use this skill here in a minute. Okay, so now number two, consider this function x cubed plus 5, which is up on the upper right-hand corner of your screen. Okay, I included the graphs from Desmos. These are just screenshots straight from Desmos right here. So what happens to the y values when the x values get bigger and bigger? In other words, as x gets bigger and bigger, as it gets infinitely large, and we say as x approaches infinity here, which means it increases without bound. So we say as x approaches infinity. And again, this arrow here means approaches. Okay, as x approaches infinity, which means as x gets extremely large, all right, what are the y values approaching? Question mark. Well, really all you have to do, you can look at the graph to determine that, and you can also do a little sign analysis. Okay, so let's look at the graph first, and then I'll do the sign analysis, because sometimes you don't have the graph. So if we're looking at the graph up here, which is here in red here, x cubed plus 5, notice that as x gets bigger, as you go to the right here, as x gets infinitely large without bound, y goes up here. Okay, it increases. It's an increasing function, and it's going to increase forever without bound. And so we say that y approaches infinity. So the y values get bigger, and we say that it approaches infinity. On the other side, on the flip side here, if x approaches negative infinity, as x approaches negative infinity, so it's getting negatively large, okay, or more and more negative, it's decreasing. Notice the function also decreases here, and so we say that the y values go to negative infinity, which means they decrease without bound, okay? Decrease without bound. It means they simply go down forever, okay? So having said that, you can even see it in the table, by the way. If you look at the table here, as x goes to infinity here, y gets, this is the x values here, y gets bigger and bigger. And then the other way, as you go to negative infinity here, okay, y goes to also negative infinity. Why? Because it's decreasing without bound. Okay, so you can see it in the table and you can see it in the graph. Okay, now how do you do it with just the function? Well, you put a either big positive number and check the sign, or you put a big negative number there. And all you have to do is focus in on what's called the dominant term. And the dominant term is the one with the highest exponent. So this right here, this x cubed, we're going to call the dominant term simply because it has this highest exponent. And when x gets large, that plus 5 really doesn't matter. Okay? So the dominant term is the term in the polynomial with the highest exponent, and it dominates the y values as x gets really large, positively and also negatively. So what we want to do is like check the sign. Let's put a big number in there and cube it, and let's check the sign. Okay, so just your x cubed. So let's take 1,000 for example, like we did in there in number one. Okay, so if we take 1,000 and we cubed it, do we get a positive or negative? And a positive number to the third power is a positive number, and it happens to be very big. So what we do is we say that y approaches infinity. All right, it gets infinitely large. That's what I'm saying. Infinitely large. Okay, so it increases without bound. Because we put a big number, positive number in, like 1,000, you get a big positive number out, which means the graph has got to go up. Okay? Now, in terms of limit notation, I'm going to switch to red here, and I'm going to write the same thing using what's called a limit notation, which is something that you need to get used to. So we use the first three letters of the word to represent this. So abbreviation for limit is LIM, and then we write as x right underneath it, as x approaches infinity, which means as x gets really, really large, given the function f of x, you got to put the name of the function there. All right, well, what is that equal to? Well, it's equal to infinity because the function's going up. The y values are getting bigger without bound, and graphically here, we can see the function is going up. So when I say y approaches infinity, the graph's going up. If I say y approaches negative infinity, I'm saying the graph's going down. That's how you interpret it. So I'm going to write that up here. This means the same thing as what I wrote down earlier, but using what's called limit notation. All right, and it takes a little getting used to. All right, so let's try it again. So as the x values decrease now, look at this. Instead of increasing, getting bigger, they're decreasing. So as x approaches negative infinity, which means they're decreasing without bound, what's going on with the y values? What are they approaching? What's going on with them? So what you do is you put a big negative number in now. So I'm going to take like negative 1,000, okay? So take negative 1,000 in the dominant term. And again, you always use the dominant term. You cube it and you just check the sign. It's a positive or negative. And here, if you take a negative number to an odd power, again, that's odd, you're going to get a negative number. And it's going to be negative 1,000 times 1,000 times 1,000. It's got to have 9 zeros. So this is a huge negative number, which means the y values are getting extremely negative. Okay, which means the y values are approaching negative infinity, and which means the function is going down. Just look at the graph in the upper right there. And then, again, using limit notation, expressing the same thing, I'm going to say LIM for limit. As x now approaches negative infinity, okay, going left on the number line there, of the function f of x, that limit's going to be equal to negative infinity, which simply means that the function values, the y values, are getting more and more negative. They're decreasing without bound, and which means that the function's going down. Look at the graph up there. Okay, when x goes to the left, when you go to the left, the function goes down. When you go look right on the number line, as x gets bigger, the function goes up. So what we have to do is understand what's going on with the y values of the function as x gets bigger to the right or smaller to the left. And what's cool about this is that you can just look at the dominant term of the polynomial. Okay, so given this one, number 3, g of x here, so let's take a look at it. The dominant term is the one with the highest degree, so let's take a look at this. And again, this is the dominant term. highest degree, so 3x to the fourth. And when x gets large, that minus x cubed plus 5, that really doesn't have much effect. When x is like 1,000 or a million or a billion, you take a billion to the fourth, that's way bigger than a billion to a third. You check it out in your calculator if you want to take a look at it, okay? So here we go. So as x gets bigger and bigger, as it travels to positive infinity, that means as x gets extremely large, what are the y values doing? Well, you substitute in a large number. So how about substitute 1,000 in there? So 3 times 1,000, right, to the fourth. Well, a positive number to the fourth is positive times 3, which is positive, is got to be positive. And this number is extremely big. So the y values are getting extremely big. They're approaching infinity. And if you look at a graph right here, you can see it. As x gets bigger to the right, the function goes up, all right, and it's going to positive infinity. So you can see it there. Now, in limit notation, you go lim for limit. So as x approaches infinity of g of x this time, so we switch names of the function, it equals infinity because the y values are getting bigger, okay, and the function, if you look at the graph, it's going up. Okay, so you don't need the graph to figure this stuff out, but I use the graph to help you understand like what's really going on. Okay, now what happens when x decreases without bound? So this terminology here, as x decreases without bound, as you approach negative infinity, so I'm talking about going left now towards negative infinity here, notice that the function goes up again. So y is approaching infinity even when x decreases without bound. So how do you know that? Well, you substitute a negative number in there, like negative 1,000. So let's analyze that. So 3 times negative 1,000 to the fourth. Well, you take a negative number, negative 1,000, multiply by itself 4 times. All the negatives cancel because this is even exponent here. So that's positive, and a positive number times 3 is positive. So this thing's positive, and it's huge. 1,000 to the fourth is 1,000 times 1,000 times 1,000 times 1,000, and then times 3. It's really, really huge. So y is increasing very fast. All right, and so we because of that, we say y is approaching infinity here because it's getting extremely big. Okay, so as x gets extremely big as a negative, all right, y gets extremely big as a positive, and that's why it's going up. Okay, now as a limit, we write it like this. So the limit of g of x as x approaches negative infinity this time is equal to positive infinity, which means the function is going up to the left and up. Okay, so these things mean the same thing, and you really have to just go home and think about it and understand what's called limit notation, because that's all over the AP exam. Okay. Now here on part C, it says how would your answers of A and B change if the function was negative 3x to the fourth? So now our dominant term is negative. Okay, so our dominant term now, dominant term, let's analyze it, is negative 3x to the fourth. Well, now we have a negative lead coefficient. Okay, so as x approaches infinity, as it gets really, really big, what kind of number do we get? So negative 3 times 1,000 to the fourth. 1,000 to the fourth is positive, but a positive times a negative is a negative. So the y values are getting really negative. So y is going to negative infinity now, which means it must be going down. And then if you take a look at it, so let's take a look at it because I gave you guys the graph. Okay, look on the far right, the upper right. So notice that as x approaches infinity, the function now is going down to negative infinity. It's decreasing without bound. How about the other direction? How about if you travel to negative infinity? So let's practice. So as it approaches negative infinity, you put a negative number in there. So let's substitute a huge negative number. So negative 3 times negative 1,000 to the fourth. Well, negative 1,000 to the fourth is positive, but when you multiply by negative 3, all right, so a negative times a positive is a negative, and it's going to be a huge negative number. So y approaches negative infinity on the left-hand side too, which means the function must go down there too. So here, Now the limits again are going to be either oh, they're both negative infinity. Sorry, they're both negative infinity because the function's going down on both sides because that negative lead coefficient. And again, you can see it in the table as well. Okay. All right. Number 4, the graphs of the function g of x here is negative 2x to the fifth, and h of x is negative 2x to the fifth plus 5x to the fourth minus 10. Well, the dominant terms are the ones with the highest degrees. Okay, so we identify the dominant term. All right. Now it says identify which is which. Well, let's just plug in some zeros and find the y-intercept here. So I'm going to find g of 0 first. So g of 0 is equal to negative 2 times 0 to the fifth, which is 0. So this one goes through 0, 0, or the origin. Okay, so right away, the one that goes through the origin is the one that's solid. Okay, so this is your g of x, solid. If I can spell that. Okay, there we go. All right, and the other one here, let's find h of 0 just for funsies. Okay, so there it's negative 2 times 0 to the fifth. All right, plus 5 times 0 to the fourth. All right, minus 10, which is obviously negative 10. So here, 0, comma negative 10 is on the graph, and that's the dotted one. Okay, so this right here, there's your y-intercept there. So the dotted one is h of x. Okie dokie, now that we established that, what's going on here? Which term in the polynomial seems to have the biggest impact on the end behavior? Which has the biggest impact on the end behavior? Well, guess what? Notice that they have the same end behavior. As x approaches right here at negative infinity, all right, y approaches positive infinity because it goes up. Both have that behavior. That's called left end behavior. Okay, let me write it out. So as x approaches a negative infinity, for both functions, okay, g of x, okay, h of x, same thing. You get positive infinity because the function's going up. All right, and then as x approaches positive infinity, the function's going down to negative infinity down here. So the y values approach negative infinity because it's going down. So the limit of either one, g of x or h of x, it's not standard notation, but I'm going to throw it in there. As you go to the right, as it gets really big, all right, that's equal to negative infinity. They have the same end behavior. Same end behavior. And if they have the same end behavior, these terms, the other two terms in h of x here, and I'm talking about the 5x minus 4, really has no impact, all right? Okay, it does not change the end behavior. Does not change or affect the end behavior. And because of that, the only thing you have to do is look at the dominant terms and compare. And that's all you have to look at. You just take a big positive number, substitute in there, or a negative number in there, and they'll tell you everything you know about the function. Okay. So when we speak of end behavior here, we're saying, hey, what happens when you go far out to the right or far out to the left? Taking big positive values or big negative numbers and see what the function does. Do the y values, are they positive? Do they go up? Or are they negative? Do they go down? And you just do a little sign analysis as I've been showing you. Okay? All right, so there are some possibilities here. So let's go ahead and record some of the possibilities. All right, I'm going to divide up these quick notes into 4 sectors. And so let's take a look at the 4 cases. Let's take a look at the lead coefficient here first. So let's put the lead coefficient up here in red. Coefficient. Okay, it either could be positive or negative. That's it. So let's put the positive cases here, negative cases here, and then the degree may be odd or even. Okay, so the highest degree of the function, which is the highest degree, it may be odd, or it may be even. Okay, and let's take a look at the cases. Okay, actually, let me switch those. Even first, that's the one. I'll talk about even case first. That's the easiest one to deal with. And then we'll take a look at the odd case. All right. So if we have an even coefficient with a positive lead coefficient, excuse me, a positive lead coefficient with an even degree. Okay, so something like 3x to the fourth, let's say. Okay, or you can say maybe 6x to the sixth, something like that. What that looks like is this right here, and then we'll write your limits. So it might have more than one relative min and max. Don't worry about that, but it's definitely going to go up. Okay, now the limits here, the limits, the limit as x approaches infinity, which means as you go right of the function, since it's going up here to positive infinity, has to go up, okay, because it goes up here. So it has to approach positive infinity. And the other side, the limit of the function f of x as x approaches negative infinity, which means as you go left, it still goes up. So it has to be positive infinity as well. So it goes when x gets large to the right, the function goes up. When x gets more negative to the left, the function goes up. Now, if you have a negative lead coefficient with an even degree, it just simply opens down. Okay, so I'm talking about something like this, negative 3x to the fourth, or negative 6x to the sixth or eighth. I don't care what, even, some even power. All right, and it looks like this. It has some, fluctuation, okay, but it definitely opens down. And so the limit here in this case of the function, which we're just calling f of x in general, as x gets really big to the right, is a negative infinity because it's opening down. And on the other side, as x approaches negative infinity to the left of the function, it still goes down, so it's still negative infinity. Why? Because it's opening down. All right, it's decreasing without bound on both sides. That's what I'm saying. As before, it's increasing without bound on both sides. Now, if you have odd degrees, everything changes. Okay, so if you have an odd degree like x cubed, for example, with a positive lead coefficient like 2x to the cubed or 4x to the fifth, something like that. All right, it behaves like this. Okay, and what do the limits look like? Well, let's go over that. All right, so the limit to the right, okay, as x approaches positive infinity of the function here is got to be positive infinity because the function goes up to the right, and going to the left changes. So the limit as x approaches negative infinity, there we go, of the function is equal to negative infinity because it goes down. So down, left and down, up and right. Okay? And the only other case we have is that if you have a negative lead coefficient like negative 2x cubed, just change the sign to negative, or a negative 4x to the fifth or something like that, it looks like this. Okay? And now the limits change. Okay, so let's take a look at the right-hand limit first. As x approaches infinity here, the limit of the function is a negative infinity because it's going down to the right, decreasing without bound. And then on the left, it's going up. So as you approach negative infinity, the limit of the function is positive infinity because it's going up. And those are the only four cases for polynomials. Again, we're focusing on polynomial functions, not rational functions. Okay, and remember the dominant, we're looking at the dominant term here. So let's put this in red. The dominant term, when you analyze a function, is the term with the highest degree. All right, there we go. And we'll do a couple more just for funsies here. Okay, check for understanding. And what I would do at this point, I would pause the video and go through this and then press play when you're ready. And then check your work. Okay? Now it says use limit notation to describe the end behavior. Okay, first of all, let's look at the graph. All right, so as x gets bigger to the right, notice the function goes up. So y approaches positive infinity. As x here as you move left to negative infinity, the y values also go up. Okay, so now what we need to do is write that in limit notation. And it says end behavior, so we have to write two limits. Okay, let's talk about the right first. Okay, the right end behavior, and then we'll talk about the left end behavior in a minute. Okay, so as a limit, so the right side, so the limit of the function, okay, as x approaches infinity, which means you're going to the right. So look right. The function's going up to positive infinity. So you interpret positive infinity as the y values are going up. Okay, and in the left side, you say the limit of the function f of x as x goes to negative infinity, decreasing without bound. So think left. All right, that also is positive infinity because the function's going up. And so when it asks you the end behavior of the graph, you always give two limits, the left and the right. Okay, is it possible I had degree 5? And no, because if you look at your learning targets right here, if they have the same end behavior, it has to be even degree. Okay, and this is an even degree function, or the dominant term it has even degree, whether it's fourth degree, sixth degree, we really don't know. Well, if we learn more things, we know. But if but it can't be fifth degree because fifth degree, odd degrees have opposite end behavior. So odd degrees have opposite end behavior. It goes up on the right, down on the left, or vice versa. Opposite end behavior. Even degrees have same end behavior. Okay, and so we're going to say no because this function has the same end behavior. Or you can say no, odd degree functions, okay? Or you can say a function with odd degree, with degree 5, let's say it this way here, with degree 5, which is odd, degree equal 5, odd would have opposite end behavior, would have opposite end behavior. And this does not have opposite end behavior, it has the same end behavior. Okay, it goes up on both sides. So it has the same end behavior. Okay, number 3. Which of the following terms, when added to the given polynomial, will change the end behavior? Well, if you add in this guy right here, if you add in a negative x to the 8th power, now that's the highest degree and it's even, so that would definitely change things. Okay, the next one here, if you add in a negative 3x to the 5th, that's not the highest degree, so that's not going to cut it. 5x to the 7th, well, first of all, the original function right here, the original function would look like this because it has a negative lead coefficient and an odd exponent. And if you add 5 to the 7th to it, let's do that in another color here. If you take negative 2x to the 7th plus 5x to the 6th minus 24, and then you add a 5x to the 7th, you have to combine these terms here, and if you simplify it, you get, let's see, 5 minus 2 is 3, so 3x to the 7th plus 5x to the 6th minus 24, and then it becomes a positive coefficient, so now it behaves like this. So it would have opposite behavior, but it'd be going the other direction. So you can select that. And adding the constants, that doesn't change anything. All right. And then here on number 4, last couple ones here, we had a lead coefficient of 1/6. LC is lead coefficient. I've got to take x and multiply it by x squared. So you don't have to multiply this whole thing out. I know I'm going to have to take x, and then in the second binomial, the x plus 4 when it's squared here. Well, let me think of it this way. Let me expand it so you make sure you understand. X plus 4 to the second power means x plus 4 times itself, right? So if you were to multiply this out, you would have to multiply x times x times x and then times the lead coefficient here. And what you would get if you multiplied these guys, you get your dominant term. You get 1/6 times x to the third power. And so this is positive here, and guess what? This is odd. Okay, so this guy behaves like this again. And so use limit notation. Here we go. All right. So we have the limit of the function here as x approaches infinity, which means to the right. Okay, and again, it's going up to the right, so it's equal to positive infinity because it's going to up. And then on the other side, going to the left, if x decreases without bound, which means you're moving left, the function is going down to negative infinity, and you interpret that as down. Okay, so that's using what's called limit notation to describe end behavior. And when I say that, you always write two limits. Okay, and this is the right end behavior here, and this is the left end behavior here. All right, and the last one here, multiple choice, which given this graph of the function here, which has a dominant, that's not the dominant term. The dominant term is negative 5x to the 6th. Okay, notice it's even with a negative lead coefficient right here. So which has the same end behavior. Well, you want to pick, again, it has a negative lead coefficient right there. So negative lead coefficient and even power. Or you can say even degree, however you want to say it, same thing. So that's not going to do it. D is not going to do it. A is not going to do it because it's odd degree here. Well, how about this one right here? So it's got -1 as lead coefficient and notice it has the same degree. All right, so it's got to be B. All right, there you go, my friends. There is lesson 2.4. Hopefully it helps you out, and hopefully I'll see you in class. You guys take care.